Allora aspetta, dimmi.
Chi è che c'è lì? Intelligente. Attacchi la wifi.
Grazie veramente per essere venuti a sentire cosa è successo queste 3 settimane. Terzo anno consecutivo a San Lorenzo, ma questa volta a San Lorenzo d'Orsino. Però abbiamo lo stesso sindaco. Quindi... è vero che questo. Iniziamo con un saluto appunto del nostro citato della casa, di questa casa del Settecento, che ancora una volta abbiamo abitato con ragazzi di 3 continenti diversi, portandoci dietro dei computer, diciamo con super computer dei poveri, ma che abbiamo usato per fare cose nuove nel mondo dell'agricoltura. Abbiamo qui amici appunto che ci hanno portato delle idee importanti in questo settore, quindi come vedete è un po' diverso, quindi siamo andati ad avvicinarci a questo mondo del collegare chi costruisce dispositivi al nostro che è quello dei dati. Quindi intanto facciamo un saluto del nostro...
Grazie, allora sarò brevissimo, solo un saluto a tutti i presenti, le autorità comprese, e porgo anche il saluto del consigliere locale della Valle Mario Tonina, che purtroppo non è potuto partecipare a questo evento. E che dire, io rappresento il comune sì di San Lorenzo, però la Web Valley riguarda l'intera valle, quindi l'intera conca delle giudicarie esteriori con i 5 comuni, e porgo un saluto a nome anche dei colleghi. Quindi ringrazio per l'ennesima volta, come l'anno scorso, FBK, i ragazzi che hanno partecipato, i ricercatori di FBK, e per aver scelto la nostra valle anche quest'anno. Dico già da subito che se la location vi aggrada e pensate di tornare, noi siamo ben felici di ospitarvi anche in futuro. Quindi buon lavoro a tutti.
Quindi un breve saluto lo farò prima in italiano e poi passeremo all'inglese, perché la lingua ufficiale della nostra scuola è l'inglese. Forse possiamo far scorrere anche un po' di foto mentre parliamo di introduzione, ma lo vedremo anche sullo schermo. Alla fine della presentazione abbiamo portato alcuni dei sistemi che abbiamo utilizzato, che abbiamo costruito, sono qui se volete fermarvi 2 minuti, e abbiamo una presentazione molto ricca, quindi e soprattutto la diamo come gli altri anni completamente in mano ai ragazzi. La novità di quest'anno, dicevo, è collegarsi al mondo della produzione agricola, pensare a una produzione agricola di qualità che si serve di strumenti del tutto nuovi, e questa è stata la sfida di quest'anno. I will have now to switch to English, also because we are in streaming and we have a number of people actually already connected. So thanks to our friend by WebValleyLab, we are streaming on YouTube channel. And after this presentation, I will be very happy to hear from our friends from the world of innovation, from the cooperative production, the experts and the friends, say if they will have comments for our work. It's a completely new experience. We also added some ideas about how to make something of our results. So you will see there is a marketing discussion, and so we would like also to open a discussion on that. So, but we should just start, and I would like to start with Eleonora. She will give an introduction, and Eleonora, and okay, Francisca, is also Victoria.
Good afternoon, and welcome to our project, Fruity Pie. We're excited to have you here. Okay. So we're going to present our project, Fruity Pie, on which we have worked on for the past 3 weeks.
So we're a group of 15 internationals from 4 nations, Italy, the US, Ireland, and India. And we've all come here for 3 weeks in San Lorenzo to work on our project Fruity Pie. The aim of our project was to create environmental solutions, environmental health and sustainability solutions, as well as food safety and food quality, using data analytics, portable spectroscopy, and machine learning. I think one of the coolest aspects of our project was our collaboration with some of the largest agricultural industries in Italy, such as Cabot, one of the largest wine producers in all of Italy, and Santorsola, the largest berry producer in all of Italy. And so before we start going into our project, we just have a quick video to show all of you summarizing it.
We will explain how our project strives to meet the need for innovation. In fact, agri-food companies striving to offer quality and environmental footprint as values need new solutions. And this was the case for both Cabot and Santorsola. In particular, with the winemaking company of Cabot, we were presented the issue of reducing costs and logistics of chemometrics, which is food analysis and understanding the chemical composition of food, enabling on-field digital precision and agriculture. In particular, a key point is to monitor harvest quality and health continuously, in particular water stress.
The way we went about doing this is by using the extremely cost-effective fruit pie. As you saw in the video, it uses a low-cost or cost-effective spectrometer and machine learning techniques. And so for the grapes, our goal was to predict the Brix index, but we also had various proof of concept experiments, such as trying to distinguish between red and white grapes, in addition to trying to distinguish between the 3 samples of the same variety of white grape.
In the case of the Sant'Orsola, we were faced with the issue of precision in fruit picking. In fact, to estimate the maturity level and to predict the day of harvest, to offer the best and uniform product, we seeked a new solution, but also to find a new in situ, non-invasive and non-destructive method to classify the berries, and most importantly, to find an objective and unbiased method of classifying them, as the human eye often perceives colors differently. So our application, through spectrometry and vision, we seek to classify raspberries into 3 ripeness categories. So early, good for harvest, and too mature, with an objective method, and also a method which is portable and non-destructive. Last but not least, it is a cost-efficient method, which can be used which can have large adoption. In particular, for every 200 farmers, for more than 200 farmers, there are more than 1,500 pickers who need to be explained how to, according to which criteria can they classify the berries. So selection by color is an issue we had to face. In particular, the vast number of varieties and the vast collection scale. So today we will present our methods for finding this solution, and we will explain how we work together to find a solution. So starting from Luis and Stefania, they will be explaining how they built the spectroscope and the various plant experiments they made, followed by the machine learning group, in which machine learning was applied to spectroscopy and also to predict the Brix index. Following, there will be the deep learning explanation of how this new and very interesting field can be applied to our spectroscopy and the spectrometer research project. This was overall crowned by the digital infrastructure, which was an important part in the project, carried out by Laura, Francesco, and Chiara. And finally, I will make some conclusions, which will include some possible marketing strategies.
So, the light that we see with our eyes is actually made up of a range of many different colors. By using a spectrometer, we can actually divide the light that we see with our eyes into the various colors that make it up. So, by using a spectrometer, we can then detect the intensity of each of these colors. So, the basis of a spectrometer has 3 main components: a source, a light source, an optical grating that breaks the light up, and finally a detector. And by doing that, we can read the spectrum and then analyze the various colors. So when we started our project, we need to consider 3 different types of spectrometry. The first one was absorption, the second reflection, and third transmission. Because we were looking at fruit maturation and ripeness in fruits, as well as leaf water content, we decided that reflectance and transmission were the most suitable. Why? Well, we have 3 advantages. The first one is it's non-destructive. You can scan the berries as many times as you want and they still be perfect. Quantitative, the second one, as you saw in the video, there's a lot of people perceive colours differently, so it's very hard for many different people to actually find out what berry is mature and which isn't. So, and third is local. By using reflective, we can just reflect off the surface of the berry and get the colour that we need. We don't need to go into the fruit, detect polyphenols or polysaccharides or anything like that. But with all of this great science, there's only one disadvantage, and that is the extent of cost. So, thanks to the Web Valley team, they gave us the opportunity to work with Jeff Warren of Public Lab, and we use this as the basis for our spectrometer. So, these are the bill of materials that we used. So basic spectrometers cost from hundreds to even €1,000. So we use a Raspberry Pi. This is like a mini computer. It's got high processing speeds and good memory, and it's also compatible with the Raspberry Pi Noir camera. Because we were looking at fruit ripeness and leaf water potential, we needed a wavelength range. So to detect what we wanted to detect, we needed from 400 nanometers to 970 nanometers. So this camera was perfect because it detects from 400 to 1,000 nanometers and at a very high resolution. Next was an optical diffraction grating. We needed to separate the light up into all of its different colors. So the traditional optical grating is just a side of a CD. So that's very cheap and it does the job. So next are the LEDs. We needed our light source. We needed something to reflect off the berry and detect whether it was mature or not. And we needed something to reflect through, to transmit through the leaf. So, because anthocyanins, the chemical in berries that cause colour, they reflect light at 450 nanometers to 550 nanometers, we decided a white LED would be the best. And for transmission, detecting leaf water potential, we use an infrared LED, which emits 950 nanometers. So we managed to build our spectrometer for less than €60, and when you compare that to the hundreds to even €1,000 for commercial ones, that's quite a big difference. So under the guidance of Marco, we were able to design our spectrometer using SketchUp, and SketchUp is a CAD program, and that allows us to design in 3D, get 3D representations, and then print in 3D. So thanks to Instituto Romero, they provided us with the 3D printer, which we could make our models from. So here on the left, this is facing our spectrometer. So that is the slit. That just allows parallel rays of light in. Then at that wall there, there's an angle, and that's where we place the mirror. That deflects the light onto the optical grating, and finally from the grating it goes to the camera. So you can see here, this is looking down from the top. There's the mirror, the grating is here, and that's where we place the camera. So once we had this built, we then tested the efficacy of the equipment. So we had to calibrate the different LEDs. So we have here, this is a white LED, it emits 400 nanometers to 700 nanometers, and you can see that's the spectrum we got there. The next was green, 560 nanometers, and that's just the green spectra, followed by red, near infrared at 850 nanometers, and near infrared at 950 nanometers. So once we calibrated our spectrometer, we had a scale that we could compare all of the spectra to. So finally, once we knew it worked, once we had it calibrated, we then tested it on the raspberries and the grapes. So again, our aim was to detect the anthocyanins, the chemicals that cause the colour, and then get our spectrum. So when it comes to detecting anthocyanin in grapes and raspberries, we use reflection and white LEDs. So in raspberries, there's 3 stages of maturation: not ripe, ripe, and overripe. And we can see here, this is one of the sense spectrums we got from the raspberries. So over the course of the project, we actually scanned over 1,000 spectra, and using that, we got accurate results. So for example, when it comes to raspberries, the Lagarai variety, we tried to see, could we detect whether they were not ripe, ripe, or too ripe. And you can see from the graph here that there was actually a really, really good correlation, and that the spectrometer was accurate enough to decipher whether the berries were not ripe, ripe, or too ripe. So that was really, really promising. And the signal processing group, the people who process the spectra, they'll speak about that in more detail. So I'm going to hand you over to Stefania, who will talk about the water potential and the experiments with the plants.
We wanted to know if our spectrometer works with different wavelengths. For this reason, we made a water stretch experiment. We used 10 plants divided in 2 groups of 5 plants each, and we watered them differently, from 0 to 100 milliliter. In the image, In the images, you can see the results after 1 week of irrigation. We found in some paper that the water pressure can be detected at 950 nanometers, and so we use a near-infrared LED to find the concentration of water. Instead, for the chlorophyll, we used a white LED because we found that the concentration can be detected in the visible spectra. We collect more than 600 spectra, 300 for the chlorophyll and 300 for the water pressure. And these are the plot of the spectra that we obtain, taking 2 leaves from the top and 2 of the bottom of the plant. And the first, in this graph, we can see that the red line and the green line that correspond to plant 1 and plant 2 that has less water are separated from the other graph, and so we can detect the wavelength of chlorophyll. The same with the water potential, because also here there is a difference between the red and the green line and the other one. We really enjoyed work detecting the water concentration, because if we can understand the real need of water of a plant, we can optimize and reduce the irrigation, and so our work is also environmentally friendly. Thank you.
So as the machine learning group, our goal was to apply machine learning techniques to determine the maturity of 3 main items: grapes, raspberries, and basilica leaves. For the grapes, what we wanted to do was classify red versus green for the proof of concept, and then classify the 3 groups of grapes, in addition to trying to predict the Brix index. For raspberries, we wanted to classify the raspberries into the 3 categories of ripeness, as Louis talked about. And for the basilica leaves, we wanted to determine the effect of water stress on chlorophyll and water potential. So initially what we had to do was take the image that the spectrometry group provided and turn that into data that could actually be analyzed. So first, we took these pixels and converted it to numbers that could be analyzed. But as you can see here, there's a lot of noise involved. So from there, what we need to do was reduce this noise. To do this, we did some various noise filtering and came up with this last graph for all the spectrum that we had that we could finally analyze.
And so in order to create our machine learning algorithm, we had to do a lot of experimentation with different techniques that are already out there and available through several Python libraries. So we started off just by experimenting with many different techniques and trying out binning and then different types of classification. And then in the end, we created a best model generator that would basically take all of the data, apply various types of binning ranging from 100 to 200 by increments of 5, and then for each of those applying a different type of classification model. And then it would go through the data several times and then figure out which of these models worked best, and that would be the output. So we first started off with TSNE to try and visualize the data and help with dimensionality reduction, as was suggested by our mentors. And when we tried this out, it kind of worked, but not really. So we had to move on to different techniques that would work better. So they recommended MDS, and we were actually surprised to find out it worked better without binning. And when we saw that it was able to sort of cluster the red and green grapes separately, we applied Gaussian mixture to smooth out the data, and then LDA to classify it. However, we wanted to see if we could get better results with other types of techniques. So using the information we got from lectures and research we did on our own, we experimented with things like PCA. So here we have a plot of how the different eigenvectors, when they're ranked according to their eigenvalues, sort of explain the variance in the data. And so this is the amount left unexplained as you go through the components. And as you can see, the first few components very significantly explain the variance. We tried applying a quadratic discriminant analysis, and it did achieve a good result. But then we moved on to support vector machines and actually got far better results. We tried with multiple different kernels, including RBF and linear. And so the linear kernel ended up being the best, and it basically just classifies the data using a line. And so for the red versus green grape classification, we got our best result with the combination of the PCA, SVM, and linear kernel using 3 components, and we were able to get an MCC of 0.69. So the MCC is basically an accuracy measure. The best score you can get is a 1, and the worst is a 0. So 0.69 was a very good result. Then we wanted to try and classify 3 bunches of grapes that we were given. And so they were all the same variety, but since they were in different bunches, there were certain properties about them that were different. And so we got our best result with PCA, quadratic discriminant analysis, using 5 components for the PCA. And since we got an MCC of 1, which is the best possible MCC you can get, we were kind of suspicious of our results. And so then we applied random labels, and we did find out that with random labels, we got an MCC of 0.69, meaning there was probably some overfitting, and is something that should be looked into further.
As we have already said, we also include in our work a project with Kavit company. And the aim of our work was to see if we can predict through our spectrometer the values that Kavit used that Kavit can detect thanks to their machine. So we use as chemical compound the Briggs index, which indicate the percentage of sugar by weight in a solution or in a juice. So we took 2 types of grapes, the red and the green one, and 3 samples for each type, A, B, and C. Both we and Kavit did the spectra of the Briggs index, and then they passed to us the values of Briggs index they found, so that we could see if our predictions were right.
So, as Bikul showed you, the data, when processed, is actually raw pixels. So, predicting the Briggs index, all of this procedure was implemented in R, on RStudio. And since we got the data using in pixels, we had to convert it to wavelengths because we found a paper which said that there is actually a relation between the wavelength and the Briggs index. So using a simple formula, we converted the pixels to wavelengths. As you can see in this graph, we adjusted our samples to number of 12, and we plotted here. So the red grapes are plotted in the black colored line, and the green grapes are plotted in the green colored line, and these are the spectra produced, and you can actually see that the difference between them and the trends, trends in the spectra across the wavelength range from 200 to 1200. We used our package PLS, which is the partial least squares, which finds a linear regression model by plotting the observable and the predictable values to a new space. In this case, we used the PCA. And the PLS analyzes the data and finds the relations between wavelengths and the Briggs index. So we can actually find fundamental relations between the variables, which are predictable and observable. And so using this data, we calculated our Briggs index and compared that with the data we received from Kavit after the false analysis. And we found that it yielded excellent results when compared to the false analysis and very close to the real values, which is at a cost which is 400 times lesser, about 400 times lesser. And using the data, we evaluated the Pearson correlation for each color of the grapes, for the most correlated wavelengths and the total range of pixels or wavelengths. And then we repeated those with both the grapes. So we analyzed the total sample and we compared those with the individual values.
So those are our results, and we did the experiment 2 times. The first time with the top correlated wavelength, and we achieved a error square of 0.93. And then the second time with all the wavelengths related to the bricks, and we achieved a error square of 0.38. So as you can see in the graph, our prediction were really good. With red grapes, the error square was even more high.
We also decided to found the range of wavelengths that are most correlated with the brick index. So the wavelengths that has a Pearson correlation coefficient higher than 0.9, and they go from, in the green grapes, from 700 to 745 nanometer. And we decided to plot a graph which shows where are these wavelengths located in our spectrum, which is these lines. And we also did the same thing for the green grapes and for the red grapes. And the interesting thing is that although they had a really different color, the range of values was nearly the same. So this demonstrates that the Briggs index can be found with a good precision both in red grapes and green grapes. We applied our machine learning models all to the Raspberry to classify them. But before, we decided to do the binning, which is a pre-processing procedure which consists in dividing our spectra in many slices called bin, and for every bin take just a particular values. In our case, the median of the values contained in that bin. And with this method, we achieved a really good result, which is MCC of 0.81, which is really high, consider our spectrometer.
And so the last part of the machine learning group was to analyze basilica leaves. So what we did was we plotted the chlorophyll in the first chart against for the spectra of the chlorophyll and the spectra of the water potential. And what we found was that there was a significant correlation between the amount of water stress and the chlorophyll, and also with the amount of water stress and the water potential of the plants.
We focused on deep learning, which is the state of the art of machine learning. Deep learning is based on artificial neural networks, which are algorithms inspired by the connection in the human brain cells. As the other groups, our goal was to predict the maturation class of raspberries, but instead of using spectra, we use pictures of those raspberries. So, in order to have a good model, we need a lot of high quality data. So we divided our images in various datasets, and the two of them were photos of raspberries of the Sant'Orsola company in their stocks in Trentino and in Sicily. And the other 4 datasets were photos taken by us of real raspberries jointly sent by Sant'Orsola to us. And we took care of dividing these photos in the 3 different motivation classes that were also provided us by Sant'Orsola. All this data was then used to develop our model.
We noticed that strong deep learning group never start to train the networks start from scratch, but they take networks that are already trained and then they apply them to the specific problem. So we took the BGG16, which is the network that won ImageNet Object Recognition Challenge in 2014. And this model was developed by Oxford Visual Geometry Group. This network was trained through 10 million different images taken from ImageNet, which is a huge repository of images, and is able to distinguish objects among 1,000 classes. In fact, this is a typical presentation of a neural network, and we can see that there is an input image and a lot of blocks. The blocks are called layers, and each layer represents a transformation that the network applies to the input image. And at the end, there is a decisional block, which has as output the 1,000 classes with the probability that the image belongs to. Our goal is to transfer the classification power of this network to our problem, and so we substitute the last layer with another one which can recognize up to 3 different classes. So we trained our network with the images we took, and the 3 final classes are early, good, and late. So if you want to actually see how it's going on inside the network, you can see in this grid the different transformations and manipulations that the network applies to the input image. And in the image on the right, you can see the input image with some transformations and how the network understands the input image. As you can see, the network is able to recognize borders and the shape of the raspberry too.
The neural network WebGG16 is trained on ImageNet image, so we start from this database 8,000 images from different kind of fluids. In our case, the neural network under the last one layer, and this one, there are 4,096 features that cannot be represented. So we use an algorithm, which is TSNE, to reduce the dimensionality of our dataset, and so to show it in a bidimensional space. TSNE was invented by Lawrence van der Matten in 2008, and it's already the best algorithm to do this thing. Okay, as you can see in this scatter plot, there are some clusters that represent data from ImageNet. In total, there are 3,000 data in this scatter plot. The green one represents raspberries, and the yellow, the apricot, and pink cherries, and the plum is represented by the blue ones. As you can see, the dots are clustered in groups, and we can see that the neural network can distinguish different kinds of fruits. In this graph, we have used a data set from Sant'Orsola, the second one, which have 1,200 images. We use just the two-thirds of the images for the training. And as you can see, there are three main groups. This one for the early raspberries, this one for the good ones, and this for late. And you can see that the good groups here is subdivided in three groups that can be for different variety of raspberries. Then we use the remaining one-third of images to validate our model. And as you can see, the dots are clustered near the previous configuration. You can see that the small stars are the same data from before, and the dots are the new data we insert in our model. Thank you.
Okay, now we have seen a lot of things, a lot of single components. For instance, the hardware part, the machine learning, and the deep learning parts as well. But in order to obtain our final result, that is the FreeDPI project, we had to find a way to merge all these single components. And so we had to find a way to create a digital infrastructure that would have allowed us to achieve our wanted results. Starting from the beginning, in our digital infrastructure, there's of course the picker that has to pick up the sample, that is the raspberry or the grape, and has to put it in the spectrometer in order to capture the spectra. This spectrometer is connected to the mobile phone app, and thanks to our mobile phone app, all the metadata and the picture of the fruit and the spectra as well are elaborated on our server, which contains the deep learning and the machine learning models. The principal characteristic of this server and of these models is that they are continuously trained. In fact, the picker not only obtains the data analysis, but also the trained learning model that is updated into the spectrometer. Oh, what did I do? No, is it? Okay. Now I leave the word to Francesco.
Okay, let's talk about the FreeDPI solution. So we have the spectrometer and we have the Raspberry Pi. But how do we get the information from this system? When you turn on the Raspberry Pi, you get a Wi-Fi hotspot. So it's Raspberry Pi unit turns on a Wi-Fi hotspot, so you can connect to the device without to the Raspberry Pi without any wired connection, just Wi-Fi wirelessly. So you can connect your smartphone or your PC. I talk about smartphone because it's the most common device to use in this situation, but you can connect also a PC or a tablet or any device capable to connect to a Wi-Fi network. And then you turn on the app or the web browser of your device and capture the spectrum and get the analysis in real time. So you get the prediction directly on the field, on the screen of your device. And it is available also without internet connection. How does it work? On the Raspberry Pi, there is a web server and a program. The program is written in Python thanks to the Flash framework, and it processes the image that comes from the spectrometer and gets the spectra and the prediction. There is the application server that makes everything work, the main program works, and all the others, and the network packages that manage the internet connection between our device, our smartphone, and the Raspberry Pi, the FruitPi solution. And so, the predictions are given in real time. So we are analyzing the fluid or the sample or what we want to analyze, and we get the prediction directly in the field without an internet connection. This thanks to the algorithms that are installed into the Raspberry Pi unit. For example, there are two methods that we have seen: the machine learning for classification of the raspberries, and the PLS regression for the Briggs index. And we can get those two methods directly on the Raspberry Pi. Also in the first place in the field without mobile connection or even a radio signal, this works because it's all installed in the Raspberry Pi. So, for example, in the first image, we can see the spectrometer working near the application. In the second image, we can see the spectrometer taking a spectra from a raspberry, and in the third image, we can see the result given on our smartphone.
Okay. As regards to the FruitPi app, it has to be said that in this case, our smartphone is kind of a display of our spectrometer. And the most important thing, one of the most important things, is that using the smartphone, it allows us to use the metadata in order to obtain the data analysis. As regards to the framework used to develop the application, it has to be said that it has been used Ionic, that is a framework based on the web programming languages. Linked to this fact, it has to be said its main advantage, that is that with only one code, we can obtain and develop the app for both Android and iOS system. So this allows us to have less development costs.
So the FruitPi spectrometer works as a standalone, so without internet connection. However, when designing the backend infrastructure, we decided to create a complete cloud solution using the Google Cloud Platform. That would have allowed us to let the user upload the data that is collected by the Raspberry Pi to a centralized database. That would allow us to collect more and more data to perform a periodic and automatic retraining session of the models to get even more accurate predictions. In order to do that in the most efficient way, we have to use Celery, which is a distributed task manager. Another very interesting feature of our infrastructure is that since it has been built using the RESTful API, it can easily be integrated to other already existing applications, such as Pika by Kavit.
So now I will be making some conclusions wrapped with some marketing implications. So, to control freshness, quality, and key product features, it is crucial to quantify the maturity level, as we have seen, estimate optimal time of harvest, and monitor continuously the product, from growth until consumption on the tables. And this can occur through a rapid and cost-effective technology, which is portable spectrometry, so FruityPie. So some features of the FruityPie solution is that it is an effective control of the fruit's quality and freshness. Furthermore, it is important proof of its safety. And also it allows to trace the status of the product, appealing to any customer, both the distributor but also the consumer. And in particular, the distributors can have the opportunity to offer different raspberry tastes because of this process of selection which FruityPie allows. So it differentiates the maturity levels and also the sweetness and the taste of the fruit. So one technology and many opportunities. In fact, both the FruityPie app and the web platform can solve some critical issues which the producer company can face. For example, some logistic problems, but also how to find a method which is more efficient and also time-saving. So starting from the first idea, it can be exploitable to promote the company, the brand, and its mission to offer top food quality and freshness and safety. So something more that I would like to say on this point is that thanks to FruityPie and a possible application on the direct consumer through the app, but also through the web platform, you can sort of create a storytelling. So the company can directly involve the consumer by telling the story of its history, but also of its production. So it can be, this is a new method of brand making, which can directly point to the consumer. Another bonus service can be for the distributor, which instead can track the status and the maturity level and classification of the fruit. A last point would be internal QC and logistics, which can be addressed thanks to the app, which allows to solve internal problems to the company.
So in essence, we take our cost-effective spectrometer to take spectra. We use machine learning and computer vision techniques to analyze these spectra, tie it all together with our app, and we get FruityPie. Thank you.
Please. Okay. So as traditionally, we are expecting. Thank you very much. We're expecting some questions from our friends. That we have some experts in innovation, and I would really love to have some comments to our developers. And so I don't know where to start. Can I start with Steno, who is actually a pivot person in the story? So we've been working together many years, and then he is the person that, while coming from ITC, has been working more with agri-food.
Thank you, Cesare. I think the work done in this summer school was really impressive. The possibility offered by this type of technologies is very interesting for our cases, for example for Cavit and for example for Sant'Orsola too. I mean, we have to define better maybe how these systems can interact with the typical managed platforms that we developed, but we are sure that we can find a quick and interesting solution for everyone.
What about the level of maturity? What about the level of maturity?
This is a nice question, Professor. I think I'm sorry that Santosora cannot be here, but if we can, as shown in this presentation, distinguish between ripe and too ripe and not already ripe raspberries, we can have a nice improvement collecting this type of fruit too, because as Santosula said, normally maybe more than 30% of the fruits get lost, and if we can teach people to distinguish with this technological structure, they can avoid these errors and save maybe a lot of fruit for production. Okay. A question for developers maybe. Did you already developed some API to interact with the technologies too, or it is possible in the future?
Francesco, Laura, would you like to comment on that? I will do that.
Yes, there are some APIs that can interact with the application and all the system. For instance, the smartphone app that we have developed has these APIs and communicates to the server the information through those APIs. And Laura can be more specific because she designed the server, the main server that can manage all those data.
Yeah, our infrastructure includes an upload page, so the user can connect to that upload page and upload all the data that the spectrometer has been collecting. And once they're uploaded, they get processed and they get saved on the main central database. And the user can also validate the samples, so make sure that the predictions are correct, so that those samples can then be used to feed the retraining models. We already have implemented some APIs here. And we're also planning to implement more.
Can I ask now Riccardo? Riccardo is developing similar things in a completely different domain, but is fighting every day on that. So can you comment and maybe ask us to our team?
Yeah. Well, I stay seated. It's very interesting, very, very interesting, and amazing the work done in these 3 weeks. I have one question that is, if I grow apples and not strawberries or grapes, how difficult is to implement a new fruit in the system? That's my first question. And the second one is if there is any competitors on the market that it's already, since it looks so interesting, if there is any other system that does something similar.
Okay, so you understand Riccardo is in the startup war every day. So I don't know, maybe Luis would like to try to answer about that?
So in terms of different types of fruit, like we tested raspberries and grapes because that's what Calvin and Sant'Orsa, that's what they were looking for. but the system stays the same. It just depends on what light you actually shine, you reflect off the apple, you transmit through the apple. So once you know what wavelength you need, it's just a matter of changing one LED and the system works. Then in terms of, are there any other devices like this on the market? The next closest one used for testing ripeness in fruits and maturation and stuff like that was cost a few hundred up to 1,000. So ours is a lower cost alternative, and I'm sure there are different ones out there. Like for example, the public lab one, they built a spectrometer, but theirs was more focused towards the environment and testing oil spills, where ours is more tailored towards testing fruit and stuff. So I believe that this is a very competitive product, and there's not much like it out in the market at the moment.
Thank you very much. Okay.
Sorry. What about the accuracy of the system developed? Do you think that can be improved, or it is accurate enough to our purposes?
I think we needed to answer. So Luis again, and maybe Vikul for the answer about the. No, Luis, you want to answer about the sensor, and Vikul about the quality of.
Yeah, the sensor that we have, it's able to measure to a couple of nanometers, so it's very accurate, and from the results that we got, you can see that it was able to clearly distinguish between the 3 different types. So a couple of nanometers is what I believe very accurate, and our camera, the Raspberry Pi Noir camera, that is a really, really high resolution for a camera.
But I don't want to throw water on that, but anyway, stability is very important. Because these machines, especially in the lab, they need continuous calibration, and of course they need also continuous calibration. So I think that you have been fighting for finding the best calibration. We found that for professional equipment, the calibration cover costs $350. So 6 times our system. So for just to give you the attention you need to that issue. So that's one point. And about the machine, let's say the algorithm, I think maybe we could want to say something.
Yeah, so for the machine learning algorithms, they work very well, as we mentioned, for raspberries. It's a 0.817 MCC, which is very high. If we wanted to change it to apples or something, we would have to run through our algorithms again, the best model generator, to figure out which the best model is. But yeah, it has a very high accuracy right now.
And again, stability along with data sets is going to be an issue. So this is a very good question, I guess. But in the amount of data, regarding the deep learning, we need a lot of data for making even better models. So there is a moment we will need to have a campaign for collecting data in the future. Okay, so thank you. Can I ask, even in Italian question, maybe is the expert who motivated most of our experiments, so especially who killed small plants in the last 7 days.
Thank you very, very much for this beautiful work for students, to WebValley and Cesare for the help that you have to have it give. And I am sure that this Fruity Pie is very important for the progress for our work in Vineyard, and is more easy control the maturation with the instrument, and I think that is a very important progress in the for grape or for winery work, and thank you very much for this emotion that I am the second time in WebValley, and it's every time a great emotion.
We have Elena. Actually, she's in the between the fantastic world of startups and also education. So I think you're very in the right point for commenting us.
Yeah, no. Actually, just a question came up to my mind, but very good. The presentation was great, guys. No, I was just thinking about the grapes. So when you have a fruit like a grape and you cannot check, I guess, every little piece. So is it possible to check the whole, you know, like what's the name, like the whole piece of grape, or you have to check on the maturity of each piece to, you know, when you think about a winery, you know, to have a little bit more time saving. I was just thinking about that.
Okay, I don't. We have seen papers commenting on that. So the difference between different position is not strong. But I would like to ask Stefania. She's been trying with the small leaves from plants. So I think the answer is more or less the same. Different.
We have not seen a big difference from the top of the plant and the bottom, and so I think it should be more or less the same with the grapes, but I'm not sure because we haven't tried yet, and so we have to improve our model.
My question was if there is any chance to save time, you know, and check on each. I don't know the name actually. Il chicco, sì, ma del chicco, acino. No, and check the whole.
So yes, so I think the point, the point is they look at least similar to us. So you check one, and you sort of an average of it, and that's the same. Maybe you know.
You can just check one.
Yeah.
Okay, I understand.
I'm not sure, but it depends on what you want. If you want to take a representative sample of the entire, because of course in a field you cannot test every single fruit. You have to take a representative sample. So this is an inquiry on which we could look in the future.
Any comment? So this is your first time here. So any comment on the organization? Yeah, the school, or do you know it?
About the presentation or the whole school? Yeah, no, the presentation was great. I think like all of them were very good at presenting. Some of them were a little bit more comfortable, and I think this is a great exercise to present, to pitch a project like yours. So in any case, this is a great exercise. I think to be there and present to a public, to people like this. So a great work, even if the project is just one.
A little advertising, actually, is starting a very great initiative also, which is going to address younger kids, and so they will be introducing to actively and learning about programming and with the science between programming. So that is an initiative, international initiative. She are going to bring it in Trentino. So that's very nice to see that here. Oh, okay. Can I ask a friend who has been working on innovation? Oh, okay. So, any comment? You've been seeing this from European perspective. So,
thanks. Well, first of all, so my side, congratulations for the work done and also for the presentation. Very, very good. So we see that the results are very so high that we are sure that the work done during these 3 weeks was very good. Also very fascinating to see that you use the Raspberry Pi, so the Raspberry firmware, to study raspberries fruit. So that's another nice point of it. I would have a few questions, but I limit myself to two. I see that the device is somehow, well, you use it in a sort of professional environment because you had like Santorsola and Cavit as customers. I would say that by using Raspberry Pi, there is also some sort of do-it-yourself approach. So I think this is something that would make it interesting. So the question is, I saw that for evaluating different aspects of fruit, for grapes there was the level of the Brix index, for then for the raspberry there was ripeness, then for the leaves of basil it was water. Is it easy in the device to change from one lab to another so that it becomes, like, for example, adaptable to what you want to measure? So if it's easy to make this change, this is for the professional use. And the second is whether Raspberry made it possible, for example, or the amount of data that you have to exchange between the Raspberry Pi and the mobile phone makes it possible to switch to Bluetooth better than Wi-Fi hotspot, which is much more like battery consuming. This would maybe allow to have a larger field test use without batteries. And then, if it's possible, to make a spectrometer that allows you to identify a Pinot better than a Chardonnay. Thanks.
Okay, so they are minors mostly, so they don't know. They should not drink, at least until tonight. Okay, so I don't know, Francesco, would you like to comment on the Wi-Fi versus Bluetooth? We discussed a lot about that, and we decided to make the fastest thing, right?
Yes, we discussed a lot about the Bluetooth or Wi-Fi connection, but we decided to use Wi-Fi connection because doing so we could also have used a web browser instead of an application, and we could have used Android, iOS, a PC or a tablet to connect to the spectrometer instead of only, for example, Android phones that have a good Bluetooth connection to the sensor devices. So using Wi-Fi can improve speed through the data connection. So we have faster data, faster result, and it's available for more devices other than Android phones. And I think that, for example, we can also use a laptop on a laboratory instead of a phone if we can use it more easily. So it is more versatile.
And I have to ask you this again. I know the answer. You are taking away LEDs on the LEDs all the time. So next. Would you make many instruments or just one?
Well, it all depends what you're looking for. Like I said, the chemical anthocyanins in nearly all fruits, they fluoresce from 450 nanometers to 550 nanometers, which is within the range of white LEDs. So basically, if you test any type of fruit for maturation, it's always going to be a white LED. But LEDs are just basically, they're really, really small and they're really easy to click in and out. So say we could implement into the device something that would make it really easy to change LEDs, say just slide them in or out. But if you're testing maturation in fruits, 99% of the time it will just be white light, so which is one single white LED which emits 400 to 700 nanometers. So if there was an exception, it would be possible to change the LED if required.
Can I ask you how many images did we use for the deep learning on the total? On the sets.
It's about 5,000 images of all the sets.
So if I remember, some of them were collected automatically by the company, and about how many from you? 2,000? So about 2,000. So actually they were very quick because they use a camera and auto segmentation of the camera. So the point is we should put the device in the middle of the process. So we can make it that we can collect these images. There's a potential also for using images from different areas. So even if they are different, we can combine from grape and berries and get the same discriminant fundamental elements. So there's a potential for creating one business after the other. This is the question. Can I ask to, even in Italian, to Armanini? So we went to see his own company. He has a completely different domain, for perhaps, but they may have similar problems in that area. So rispondo di una parola.
Sì, scusate, io devo denunciare la mia ignoranza, ho compreso in buona parte, ma non tutti i dettagli perché ho delle difficoltà linguistiche, quindi comunque penso sia un lavoro molto importante e da quello che sono riuscito a capire per la mia capacità di comprensione ritengo che uno strumento di questo tipo possa avere applicazioni infinite anche nel prodotto che realizziamo noi come azienda. Ritengo che possa essere in futuro sicuramente un qualcosa di innovativo che possa dare al consumatore un valore aggiunto che sia sulla conservabilità come abbiamo ipotizzato oppure su alcune altre caratteristiche organolettiche che il prodotto contiene, che è difficile percepire se non tramite un'analisi di dettaglio. Quindi complimenti anche da parte mia, ritengo che sia un lavoro importante di ricerca e continuate in questo senso. Grazie a tutti.
I will close with an international view by Giorgio. He is an expert in branding and marketing, and I guess he made a crazy move. He spent the last night with us, so he didn't know. He thought we would stay and watch the Italy, France, Germany, and then go back with the beer instead of 4 o'clock when we were still there preparing. So, but I think you grasped the concept. So maybe you can give. Would you think this is internationally interesting to me?
First of all, I have to say that I'm a bit more involved than the other people because I've seen them working in the last hours. So I'm slightly biased on the positive side because the difference between what we saw yesterday night at 10:30 and what we say today is immense. It's a completely different story that I've heard today, and not being a specialist of this field, I've understood it much better today. I think the application is absolutely interesting. Food is an area where people are interested in the quality, in the maturity of the product, in the taste, and the connection are very interesting. So far, the main dimension that has been used was the location, tracing the product, where does it come from. Now we're trying to add a completely different dimension, which is time. And that's absolutely interesting, that's fascinating. If I had the money, I would put money in a startup like this, because it's absolutely fascinating to find a way to understand whether the product that you are producing or that you are consuming is proper, has reached the right level of maturity, has reached the right level of quality. Then the logistic issues of coming from the field to the mouth of the consumer, it's also helped by this application. So I think it's very, 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 very promising and very interesting. And I have to add again for the young boys and girls here that I was impressed because they're very young and it's not easy to stand in front of other people with 18 or 16 or 17 years and try to convince them in another language in most of the cases, and they did an excellent job. So I think that it's a very promising story, and as Eleonora was saying, storytelling is becoming more and more the main focus of every marketing effort, and main process to build the brand, to make it interesting for the consumer. And using these tools, you can build stories that are very interesting and absolutely close to the product, which means we're not telling stories like about the room Pampero, the most rum in the worst bar in Venezuela, in Caracas, which doesn't mean anything about the product quality. It's an invention of an advertising agency. We are now talking about product features, the core product features. So I think it's very, very interesting. And I'm happy to have spent the night like I did yesterday night. Thank you.
Ok, so adesso parlo per gli amici italiani. Come avete visto abbiamo fatto uno sforzo per collegare assieme quella che è il mondo della ricerca e insegnare a fare ricerca al mondo del creare innovazione, creare nuove idee e quello che dimostra quest'anno è che sicuramente si può fare. No? Abbiamo guidato molte nuove idee di ricerca che riuseremo nei nostri laboratori da delle domande tecniche precise, dirette. Giorgio faceva una visione del futuro molto promettente, quindi può darsi che abbiamo anche aperto per noi delle nuove opportunità. Nel farlo abbiamo imparato assieme ai ragazzi, dei nostri colleghi in queste settimane, cosa vuol dire affrontare delle cose che non si sanno e che sono complicate su tanti piani, no? Quindi non c'era soltanto sistemare un database con la cosa più interessante e innovativa, ma andare a provare deep learning è una frontiera che ci troveremo dentro in qualunque oggetto tra qualche anno, controllare l'interazione tra questo dato che ti scappa tra le mani, perché mentre guardavamo la frutta questa cambiava e scambiava di colore, di faccia, di probabilmente di sapore e sappiamo che la storia del vino è anche questa, no? Un vino è controllato ma lo vogliamo anche vivo, insomma, ci sono un sacco di cose importanti e interessanti da fare. Ecco. Allora, per i ragazzi, for our students, for our colleagues, I think we just have to say thank you to the tutors and the friends who have been working together for these 3 weeks. And some of them are hidden by with the other kind of equipment, any kind of equipment. So thank you very much for your time this week. I think we had a very good time together. Another time, 16 years. And he knows us much better than my person here in the room because he has been following our story for 10 years at least. So.
Well, I wanted to thank you to the teams, the tutor, the scientists, the local sponsor as well, and thanks to you, Cesare, because all of this can be actually actual and is very important for FDK and for our territory, and not only. I want also to congratulate with the students. You did an impressive job, not only for the competencies and the scientific approach that you put in your job in these few weeks, but even because you leave the place, you worked hard, I guess. You stay together, you collaborate, you present it at the end in a very good way, both in a scientific approach at the beginning, and then with some marketing, appeals that is always very useful to understand better how applications can be completely have a place in the market. Part of that, I would like also to thank you, the cooperative organization CAVIT and Sant'Orsola, to be partner of this project. I believe that the cooperatives need to keep this alliance with the scientific research centers and starting from the educational issue till the ability to find new solutions and transform even prototype application in industrialized products. So I think, Cesare, that this will, I hope that even for next year we will have the opportunity to have other cooperatives collaborating with you on your next summer camp, and best of success to everybody.
Thank you. Thank you. This is unofficially closing, unofficially because we have would like to show you our poor man supercomputing that's here. So Matteo will be presenting about it if you like it, and if you want to, until it works, Luis will show a real life example, and please stay with us. We are going to Castelmani to have some refreshment immediately after. And thank you again to all the friends for doing that again. I don't know, 17 last year, so we have to think twice. But Beppe, our director Beppe will say is a prime number at this point. Okay. Okay. There are two persons actually made a lot of work on that. So Giuseppe and Claudia for management. So thank you very much. Okay, they believe they're students at this point. And Raquel is young Rachel. Thank you for taking care of us. And some people here, including Michele, which is the farther praise possible from the stage, and Marco, which is more closer, so they work a lot to prepare it together. Valerio, first time for ever, so he totally destroyed. Thank you so and many other friends. So thank you again for working together, and enjoy the rest of the night. Ciao.